Well, good evening, everybody. I'm glad you're all here. My name's Rick Stein. For those who don't know me, I'm the interim pastor here at Avon Lake Presbyterian Church. And it's my pleasure to welcome all of you and to introduce our member of the congregation, Lynn Bondurant. And so this evening, I want to share a little bit of information about Lynn. He likes to tell everybody he grew up near the home of Jesse James in Missouri. And that during his childhood there, he spent many hours walking in the woods, and he got a lot of knowledge of that and loves nature. And he'd lay out at night observing the sky and naming all the constellations. And that would become, they both would become his good friends throughout the rest of his life. Lynn is an educator by trade, serving in many roles as a biology teacher, a principal, a planetarium director, curriculum coordinator. He served on the school board in Avon Lake, and he was a member of the board of trustees of Park University. He's also had experience working in museums. He was the first education officer at the Smithsonian's National Air and Space Museum in Washington, D.C., and was also on loan from NASA's Glenn Research Center to the Great Lakes Science Center to help them get organized and help them finish putting their exhibits together for the grand opening. And during his career at NASA, Lynn worked at the Goddard Space Flight Center in Greenbelt, Maryland during the Apollo program, and he joined Glenn Research here in Cleveland in 1981. He's visited every NASA center at least once. And during his tenure at Glenn, he created many programs that had a national impact on space education. As an example, he led a team at Glenn to create the Science, Engineering, Mathematics, Aerospace Academy, called SEMA. I believe that's SEMA, okay. And the program, it was to attract the underserved students to get them excited about a career in science. In 2006, the SEMA program was selected as one of the top most innovative programs to impact the community in a positive way of any city, state, county, or federal program in the United States by the Ash Institute, which is part of the Kennedy School of Government at Harvard University. For his effort with SEMA in the year 2000, Lynn was honored by receiving the Dr. Martin Luther King Jr. Award for Education in the state of Ohio. And also for 1 year, he was on loan from the NASA Glenn to help the families of the Challenger accident, help them establish a Challenger Center for Space Education in Washington, D.C., and he traveled there weekly. And I just touched your screen here, so things just started moving back and forth. So anyways, my bad. He's also co-chair of the Cleveland Bicentennial Education Committee, and in his role, Lynn was able to get a 2-mile-long asteroid named Cleveland in honor of its bicentennial, and co-authored with Cindy Hill the book, Cleveland's History Through the Message of Starlight. Many don't know that Lynn loves classical music and theater productions. He has done several things in this area, like narrating 2 children's concerts with the space theme for the Little Orchestra Society at Avery Fisher Hall in the Lincoln Center in New York City. And in 1984, he worked with Vincent Dowling, director of the Shakespeare Festival, to change the location for the play A Midsummer's Night's Dream from the Earth to the surface of the moon. Lynn has received many honors for his accomplishments, but 2 of them highlight his impact on education. In 2004, he was inducted into the North Kansas City High School Hall of Fame, and in 2016, he was inducted into the NASA Glenn Research Hall of Fame. So we've got an expert here tonight. He's certainly no slouch. But I've known Lynn for a long time through work in the presbytery, and we're excited that he and Kay have been members here for almost 2 years, and they bring a lot to our congregation. And so it's my honor to introduce our friend and yours, Lynn Bondurant.
Well, thank you, everyone. I'm delighted to be here tonight. It's really an honor, especially at the church here. I do want to mention also that we've arranged that tonight we're streaming my presentation to the entire presbytery, which goes almost all the way to the Pennsylvania border. So hopefully some of those folks will be joining us as well. I couldn't have done tonight if it wasn't for a few people, and I just want to recognize one, Jay Knox, he's in the back. But Jay helped me with the slides. We modified the slides so we could use them very effectively here in the church. Emily Oliva, who's the Christian Ed director here, she really helped developing a lot of the materials, and I hope you pick them up, and we'll talk about those later. And then Rick is always a great support. And then, there's other people that have helped as well, like Paul Buteri's in the back working with the sound system right now. And I also wanted to thank Josh Dahm, who arranged for the streaming of our presentation tonight. So if I suddenly put my microphone down where you can't hear me, I hope you will raise your hand or something. I think tonight, as I thought about tonight, and I've thought about this, I helped a lot with the Avon Lake Eclipse Committee as well, that this is really a very special occasion and a very important event. And I think we're so fortunate to have it. And you'll see later how rare it is for us to have a total eclipse of the sun. And we can look at that. Whoops, let me go back one here. Whoops, I lost that again. Well, anyway. Let me see if I can read over here. Oh, my goal. My goal tonight is to tell you what I know about eclipses. And I think this is important. I think a lot of people just want to go out and look at the eclipse, and they don't understand the history. They don't know what can be done and all those sorts of things. So that's what I hope, and I hope you leave here tonight more eager to see the upcoming eclipse than we have, that maybe you would have not had if you hadn't come tonight. And Jay, I'm sorry, I'm going to have to wave my hand here because I can't see. But anyway, the word eclipse is kind of interesting. It's a Greek word, and the Greek word for the Greeks was Helios was the sun god, and Helios went across the sky, and every once in a while Helios disappeared on him. And the word eclipse means abandonment and things like that. And so really what we had was an occultation of it's when a big object moves in front of another one. That's called an occultation. And that's what happened. In fact, the day before we have the eclipse next week, next Sunday at about 12:30, you won't see it, but the moon is going to move in front of Venus on its way to the eclipse. And so it's going to be kind of interesting, and I didn't give you the directions because Venus is pretty close to the sun, and I don't want anybody to injure their eyes by mistake by, looking at the eclipse. So eclipses are important, and I'm just amazed at how the stories go with these eclipses. In fact, for many centuries, the solar eclipses have historically been viewed as omens that are destined to bring disaster and death. And even today, people still don't believe in that solar eclipses are nothing but evil. But it's more than that. Because through history, we've learned that an eclipse, like a total solar eclipse, is more than a breathtaking event, but it's also an event where we can learn much more about the sun. And So that's why it's kind of fun to see these. And now this is it's kind of hard to see the picture, but this is a picture of an eclipse crew. It's a total eclipse expedition where you get a group and they go off to study the sun. And there's a great book out, and it's hard for you to see the people, but I'm glad I don't live back then. Look how they had to dress. My gosh, it was just terrible. Long thing. There's only one person. Jay, could we go back one slide, if that's possible? The only person I think that was dressed right is this person, the second person here on the right. See him? He doesn't have all that garb on. You may not know it, but that's Thomas Edison. And Thomas Edison went to the 1878 eclipse, and what he invented was called a taximeter. And what he was hoping to do was to point it at the corona and measure the temperature of the corona. And he set his experiment up, and it was kind of interesting because they assigned him to set his experiment up in the chicken coop. And so he was all set up. But when it came time for the eclipse, it was kind of funny because it began to get dark, and those doggone chickens wanted to go to bed. And so they came in, and the wind came up. He was able to take one measurement, but it was so far off, nobody ever looked at it. And another person there, and if we can have the next page, yes. There's a book called The American Eclipse. And I would encourage you to go home and get your Kindle out, or go to Amazon.com, and it's only a few dollars. But it tells the story of the 1878 eclipse, and it's a dramatic story. 3 people are featured. One, I mentioned already, was Thomas Edison, and then there's Watson, James Craig Watson. He was a professor at Michigan University, and he was out looking for the planet Vulcan. Now you see, people had studied Leverrier, who was a French astronomer, pointed out that there was discrepancies between in physics, the Newtonian physics, there was an error in the time that the moon, or that Mercury went around the sun. And he attributed it to a tiny little planet that he called Vulcan. And what he thought was that little planet would tug on Mercury and cause those problems, to be taken care of. And so Watson looked, and again, he declared to everyone that he did find the planet Vulcan. Got world recognition for finding the world Vulcan. But come to find out, it wasn't there. Because later on, it was explained by by Einstein. And Einstein created the general theory of relativity. And what it pointed out in that theory that he had, that they're gravity-based wells. In other words, every massive body, like a star, is kind of in a sinkhole. And so what happens, it bends light. And so what people were observing that thought was the error was where Mercury was, but it was due to where its light was bent. And so it was really that error that once Einstein got his theory published, that finally confirmed his entire theory of general relativity. Next slide, please. Okay. Why are solar eclipses so important to study? Well, there's lots of reasons. One, and I only picked a couple, but it was interesting that the gas helium was discovered on the sun 30 years before it was found on Earth. 30 years before. And because it was named in honor of Helios, the Greek god that took the chariot across, the Romans had Apollo, but they had Helios. That's where the term helium came from, based upon where the gas was produced, or in honor of the planet or the god Helios. And it's interesting that MRIs depend upon the use of helium. And to run a typical, and I think every year right now we're having about 40 million scans with an MRI. 40 million scans. And each one of them takes 17,000 liters of liquid helium during its lifetime. And I think the cost of helium right now is anywhere from $30 to $50 a liter. So you can see that it's expensive. So helium was an important thing. The next slide, please. The second thing is, let me make sure I know what it was. Okay. All right. The next thing that I want to mention when I saw the slide was that eclipses help prove Einstein's general theory of relativity. And to do that, you can't do it during the day. You have to have a dark sky. And so it was a perfect time during the eclipse that Einstein calculated that the light would bend that stars by 1.75 arcs a second. Now, an arc second is 1/3600th of an angle of 1 degree. There's one, and so he predicted a 1.75 arc second shift. Now, what that means is, if I took, and we went out to do it tonight, we would walk about 2 miles with a board or whatever, and then we'd stick a 1 inch, after we walked that distance, a 1 inch high peg right there, and that's 1 arc second. Can you imagine that? Almost 2 miles away, and it only has about 1 inch. And so Sir Arthur Eddington was on the eclipse, and they decided that they would use, in other words, 1915 is when Einstein came out with the theory, and so here it was 1919, and Arthur Eddington and his group went out to photograph that night. You can't do it at night because there's no sun, and you need the sun, to do the measurement. And so they went at night, and I don't know if you've ever seen the Pleiades, but Taurus the Bull, the constellation, but it's shaped like a V. Those are called the Hyades. And so what they did was they photographed the Hyades at night, and then they would then compare it with the shots that they had during the daytime. And that proved that Einstein's theory of relativity worked. And it changed the whole world as we look at what the universe is like. Next slide, please. And you can see that slide's kind of hard. It's not very big, but you can see that the light is bent, and that's a new field of astronomy, is gravity astronomy, where people are looking at objects behind other stars because the gravity of the star causes deflection. So anyway, I hope I got all that right. I remember one time I was up at Princeton Seminary for a meeting, and so one lunch I decided I walked to Einstein's home, where he used to live. I just wanted to see what it was like, and I got there, and I couldn't go up on the porch, darn it, but they had a sign on the gate, you couldn't go in. But for about 10 minutes, I rubbed my feet, and so I feel the rest of the day I felt smarter than everybody in the room. But anyway, so that's kind of an interesting way to look at. So I tell you, the knowledge of the universe is changing so fast I can't even keep up with it. Now they're claiming it didn't have a creation. I don't know what's going on, but it's kind of hard. Next slide, please, Jay. Now here, it's kind of hard to see these two, but the orange one over here is the sun, and up here, that's a sunspot. In other words, the photosphere is right here, and then above the photosphere is the chromosphere, and here's the corona out here. And so those are the three things. Now I want to warn you, I just advise you to do something. After the eclipse, don't throw your glasses away. Keep them in a drawer someplace, because if a sunspot is 4 times the size of the Earth, if it's 4 times the size of the Earth, you'll be able to see it with the naked eye. So, and sometimes they're even bigger than that. So that's kind of an interesting thing. And Then the one on the right talks about, you can see the one on the right over here, if I can find a button. I don't know where the button went. Well, there it is. Here's the sun. Look at this, right over here. And it goes out here, and this is called the solar ridge. This is the solar wind. This is the corona. Now, that's a very important thing to know about the corona. The corona is constantly sending things out into the universe. And if you took everybody try this, take it and blow up breath. Put your hand about 4 inches away and blow a breath. Okay? Now move it a little bit further and blow the same way. And then put it a little bit further. Okay, and then it stops. You can't feel it anymore, can you? So what happens, the solar wind goes out in space, and about 1 billion miles or so, it can't go any further. And so what it's done, the solar wind has actually put the whole solar system in a bubble. So we live in a bubble. It's called a heliosphere. And it's interesting that heliosphere helps protect us from cosmic rays and things coming into our solar system. And I just think when God created all this, it's just amazing how he fit this and that, and, everything together. And it's just amazing. And they keep finding more and more, as I mentioned earlier. So the solar wind can cause a lot of problems. And let me just go to the next slide, if you could. I think it may, and the next slide, please. Well, it's hard for you to see, but this is the corona out here. Look at the corona. It's constantly, and if you can go on the internet, you can actually get shots of it, pulsating and sending everything out. Next slide, please, Jay. Next slide. And you can see the temperature range on this particular slide is 1 million to 20 million degrees, and it's blowing off materials. And the fastest materials can get to the Earth in 15 to 18 hours. And so all sorts of events can happen. And the next slide, if you could, is an interesting slide because it reflects something that happened in 1859, if I'm not mistaken, if I can find it here. 1859. There's so much detail here, I just want to use a note on this one. But there was a person by the name of Richard Carrington, and there's his picture up there. I think he owned a brewery, and he lived on an estate, and he had his own observatory. And one morning in May, he got up and went out, looked at the moon, and what happened, everybody back then was sketching the sunspots. I used to look at the sunspots and things, and they would look at the sunspots. And he noticed while he was doing that 2 of the sunspots suddenly got real white, and they stayed that way for about 5 minutes, and then they just shut off. But that night on Earth, the Earth lit up. Almost the whole Earth had aurora, the northern lights, even going down to the equator. Everything was lit up. And for the telegraph, it began to shoot out sparks, and it was setting papers on fire. There was so much electricity, they didn't need anything. It would operate all automatically to power the telegraphs. So that was a very humbling event that occurred that night. And a lot of people actually thought that the Earth was ending its life, and but Carrington really found out, this is called the Carrington event, and they really found out what it was, and that was those sunspots that were giving off flares that had the energy equivalent to 10 billion atomic bombs. 10 billion atomic bombs. So it was interesting also in 2008, the National Academy of Sciences took a look at this and tried to make a prediction. If they had to repair everything, they estimated it would cost between $2 and $3 trillion to repair all that. Now, there's one person in this room, I won't mention her name, but she's always thinking about worrying about things. Well, sometimes I sit out in the front and I sit under a maple tree, and one of my things I love to do is to look up at the clouds, and this layer is going that way, and way up above another layer is going a different way. And sometimes I try to capture the speed when they go across the ground. If you set it up, you know, here and there, you can determine the speed of the clouds and things. And it's hard to believe that those little clouds you watch weigh 1,000,000 pounds. That's another thing that, wow, you know, that you don't know. But so it's interesting that we've got to do something about our grid. What would happen if through terrorists or through one of these geomagnetic storms, they knocked out the power grid? What would it be like in Avon Lake if we had no power for 5 years? You'd have no heat, no water, no electricity. Can you imagine what the world would be like at that? So I think we need to begin to develop new ways of looking at things and doing things with our grid. The next slide, if you please. Oh, is it already up there? Let me see. Yes, this is the next slide. I didn't know if you know about the National Oceanographic and Atmospheric Administration, but they have a part of it that's called, this particular one looks on solar wind, and it studies all the events that are related to the sun like that. And they can, then they issue, next slide if you could, they issue warnings, and this one you can't read, I'm sure. But recently in February 21 and 20, we had a magnetic storm that hit the Earth, and it was a strong one, and it was almost powerful enough to knock a lot of stuff out. You got to watch the satellites, GPS, all those things, so that they don't. The only thing that saved us is that the solar flares were pointed, not pointed directly at the Earth, but at an angle. And if they had been pointed at us directly, like the one in 1759, we'd have had a big storm that could have been quite disastrous. So our sun is important to study in many, many different ways. And Jay, may I have the next slide so I can see what it is? Oh, this is one of the posters that NASA produces. Do you see all those satellites there? All those different satellites? They're all studying the sun because we need to know more and more knowledge about the sun. And in the next slide, if I can get that, please, is the solar probe. It's the Parker Solar Probe, if I remember. Yes, Parker Solar Probe. And it's interesting. It was on a 7-year mission. It was launched in 2018, and it will be over in 2025. And every year it goes over the sun 7 times, gathering information. And it's interesting, on its last pass by the sun, it's going to be traveling 430 miles an hour. Can you imagine traveling 430 miles an hour? 430,000 miles an hour. And now you talk about rapid transit. Do you realize that you could go from Washington, D.C. to Philadelphia, Pennsylvania in 1 second? Now that's how fast it's traveling. And it's collecting all sorts of information. It's even changing the way we think about the sun. And they're going to be publishing a lot of results about it, but I think it's really something else. Next slide, if we could. Now here is, I'm going to start now with the eclipse itself. And you notice here, what I did one time, I sat down, and NASA has a publication that takes you can go back 2,000 years in time. I mean, you can go back to the year 2000, before the Common Era or Christian era, and to today, to 3000 Christian era or Common Era time. And do you notice the first one it was in the year 1, I think? Let me see. March 1st. Okay. That was eclipse. And then going on down, that was in the year 191, 2, March 1st. The next one was 411, then 619, and then we come down to 2024. And our next total eclipse in this area will be in the year on September 12th, 2444. So total eclipses only occur about once every 300 years or so in an area. And so it's kind of interesting. And also in the last time that, in 1806, when we had our eclipse, Tecumseh was, kind of the chief of the Shawnees, traveling all over the country, getting all the Native Americans to unite. And, but shortly after that, they had the Battle of Tippecanoe and Tyler too, and they moved all the Indians west. But also in 1806, they named the corona. And it was a Spanish astronomer, and I can't pronounce his name, so he was just a Spanish astronomer. Next slide, please, Jay. Now, here are the phases of the moon. And you're going to begin to see that the moon is very critical to when we have eclipses. And you can see on my right and on your right, you don't see anything right there, that black spot, and a blank spot. Well, that's where the new moon is. And then it goes to first quarter. It goes to waxing crescent, first quarter, gibbous moon, full moon, waning gibbous moon, third quarter, and back then to a waning crescent, and back to a new moon. So a new moon is very important. Next slide, please. And if you can see what I did, I'm always going off and doing crazy things, but I thought you might like to know what it looks like on the moon when you look at the Earth. And so what it looks like, the moon would be, the Earth in the lunar sky is about 3 to 4 times bigger than our moon is in our sky. And it's pretty much located in one place. It does move around in a kind of an ellipse because the moon has different speeds as it goes around. And so when we have a full moon here, you have a new moon on the moon. And when you have a new moon and the lunar sky of the Earth. Okay, next slide, please. So what happens, and this one here is pretty faint, but actually we're walking around the Earth. I brought my Erlenmeyer flask with the Earth inside, but what I was trying to point out, the Earth goes around the sun in a counterclockwise direction. The moon goes around the Earth in a counterclockwise direction. And so you have the Earth rotating, the moon going around, and the Earth orbit around the sun is counterclockwise as well. Now, if I say this floor right here, that's the ecliptic. That's the path of the sun and the Earth around, the sun. So the sun is right here. Let me try to get down here. So you can see the red line, hopefully. That's the floor I was walking on. And the black line is if I went to the center of the Earth and turn on a bright light, that's the Earth's equator in the sky. Okay? So when it goes around like that. So that's important to know, well, when you're going around the sun and the moon. Okay, next slide, please. Okay. Now here's a slide that's kind of hard to see too. But you can see 3 white objects there. That's the Earth going in a counterclockwise direction. Then notice the moon. Right over here, if I can get the moon and the sun and a star all lined up, well, it's just a moon and a star. Well, you have the Earth, a moon, and a star. And it takes 27 1/3 days for the moon to get back to that position where it's looking at, from the Earth, the moon, and then the distant star. So that's 27 1/3 days is a period of time it takes the moon to go around the world, around the Earth in terms of the stars. But to go from phase to phase takes 29 1/2 days. Because in that time period, the sun has moved a few degrees from where it was before, so the moon has to move a little bit farther to catch up with it. Okay, next slide. And the next slide are just the definitions, where you can see that the synodic moon and the sidereal moon and what their times are. So 27 and a half, 27 and a third, 29 and a half days. So remember, we're going to come back to that. Next slide, please, Jay. And here again, can it be made large? Oh, I'm sorry. It's already there. This is an anomalistic moon. Now, what that means, an anomalistic moon, you know, as it goes around the Earth, its orbit is not circular, but it's somewhat ellipse. And so at one time during its ellipse, it's closer to the Earth than it is at another time. So it's called the anomalistic moon. And what does it say for the number of days? Is that 27.5 days again. So that's important. Perigee is very important. Notice up here that the Earth, the orbital velocity of the moon is about 2,100 miles an hour around the Earth. And notice that perigee, that the moon can be 225,000 miles from us, and if you're at apogee, it's 250,000 miles. And so successive perigees, again, 27.55 days. Next slide, please. Now here are the two moons. And one of the things I do on occasion, they have what's called a supermoon. Have you ever heard of that term, supermoon? And they have a micromoon. Okay? The supermoon occurs when the moon is at perigee, and the micromoon occurs when it's at apogee. Now, next slide, please. And you can see here, look at that you can see that it appears to be about 12% larger and 40% brighter. So a supermoon, it's kind of fun to go out and watch it rise over Lake Erie, because the moon is just so bright, and it's just fun to see. So that's important, because you want a moon that's big, because it's got to cover the moon. I mean, it's got to cover the sun. Next slide, please. And here again is the Earth going around the sun. And you can see that as it goes around the sun, the Earth is traveling on a mean about 67,000 miles an hour. Now remember, the moon's going around the Earth about 2,100 miles an hour. And this is going around the Earth about 67,000 miles an hour. And rather than apogee and perigee, we now have, we have perigee and apogee. Now we have perihelion and aphelion. Remember, by now, you know, helion refers to the sun. So perihelion's where you're closest, aphelion when you're farther away. And notice that we're closest to the sun in January than we are in June. So that's hard to believe, or July this says. And so you can see that at perigee we're 91,400 miles and from the sun, and in aphelion we're 94 million miles. Next slide, please. So what happens here, you can only see there's a difference in about 3.6 bigger. So it doesn't change that much. Next slide. Now what's amazing is that the sun is about 400 times bigger than the moon, okay? Do you see the moon's diameter there and the sun's? If you multiply the moon's diameter times 400, it gets close to what the diameter of the sun is. But at the same time, the sun is 400 times farther away than the moon. And so by accident or consequence or whatever, they're both the same size in the sky. And I think that's remarkable, except, you know, when they vary from being close and far and all that. Okay, next slide, please, Jay. Okay. Now, I hope you can see the word path, P-A-T-H. Do you see that, P-A-T-H? And then up here it says also, these are the solar eclipses from the year 2000 before the Common Era to 3000 in the Common Era. And this is, notice, in all that time, in 5,000 years, we have about 12,000 solar eclipses. Can you believe that? In 5,000 years, we have about 12,000 solar eclipses. And it's interesting. Notice the most common is a partial eclipse. So when I ask you later, what's the P? Partial eclipse. And we're going to see what those are. The next is an annular eclipse. And then the next one was a total eclipse, and the last one was a hybrid eclipse. And here's what they look like. Here's what the partial eclipse looks like. And everybody that's not in the totality path, that's all they're going to see is a partial eclipse. And even if it gets almost all the way full, it's not going to be dark enough to see any difference. The one in the middle is where you have a moon that's more towards aphelion, or apogee, and so it's not big enough to cover the sun, and so you're going to see this in just a second, but you're going to have a ring around it, and it's called an annular eclipse. And then the third eclipse you see right there is a total eclipse. Okay, next slide, Jay, please. And this is pretty hard to see, but over here is the sun, there's the earth, and and then the shadow coming off, and then you can see the shadows going down. Whoever did this drawing didn't do it accurately. That's called Anthumber next there. Next slide, please, if you could. And so, what about it? What do we need for a total eclipse? Well, number one, you need a new moon near perigee, okay? New moon, new perigee, that's important. The second one is, at the same time, there's a new moon. So we need a new moon, we need it at perigee. And the third thing we need is at the same time that the new moon is near one of the lunar nodes. Next slide. Next slide. Now here's what the lunar nodes, remember I told you this was our ecliptic? But what happened years ago during the heavy bombardment period in the past, which was maybe 40 million years ago, either some object came by and it knocked the moon into a 5-degree tilt. So the moon, as it goes around the orbit, can be up 5 degrees or 5 degrees. In other words, if it was at feet, it'd be 5 feet up here, goes under the floor, and it can go down 5 feet down below. Do you see that, how it's up and down? And that's the lunar nodes. Okay, next slide, please, Jay. And what we'll do on the next slide. All right. And so now we have the Draconic month. And that's where the amount of time it takes to go from the ascending node back to the ascending node. And you can see how many days that is. Should be about 27.2 days. And the eclipse seasons are the result of the moon's orbital plane. Okay, next slide, please. And you can see when a new moon or full moon is within a certain distance from the lunar node, we get eclipses. And what happens approximately every 6 months? Each pair of eclipses is an eclipse season. Next slide, please. Now look at that. It's kind of hard to see. But up here on April 8th, third one down, we have a solar eclipse. And so they said about 6, that'd be October, November, December, January, February, March. And we come down here, where's March? Oh, which one was I doing? April? Oh, well, let's go to the April one. So 6 months, May, June, July, August, September, October. And so you can see the next one is October. The next solar eclipse is October 2nd. Do you see how the eclipses are about 6 months apart? And it gets more complicated, but I want to keep it pretty simple. But that next slide, please. So every 6 months. So what happens is that what I want to happen is I want the moon, the sun, and the earth all to be on this board right here. Do you see that? And those are the two middle ones up here. Let me do this and this. So look at that. See how straight they are? So you can have a solar eclipse here, or you can have a lunar eclipse here, solar eclipse and lunar eclipse. But notice here the shadows above or below. See, this is below and above. This, okay? So below and above. And so you have to have the eclipse season to get an eclipse. Next slide, please. Okay. And here are the times and the dates. And over here, here it is. Here's our ecliptic. Remember, that's the floor. And here's the tilt part. That's the moon's orbit. Okay. And then notice the moon comes up. It's into, well, the degrees from here to here. What happens is that you get these. So over here, it tells you if you get this, you're going to have a total eclipse. In case of the node from right there where it touches to 9 degrees on either side, you're getting a total eclipse. Then if it's more than that, like 11 to there, you get a total or a partial, then a partial, and then when it's more than 18 degrees or on each side, you don't get anything. So that's one of the things that determines when we have eclipses, is how close they are to that node that comes out of the floor and up, back into the floor and below. So as long as it can be up here on the level part, you're going to have an eclipse. Next slide, please. All right, so here it talks about all of the different kinds of eclipses. The partial eclipse is interesting in the fact that it's not in the central path, but it's outside of the path, and it's in a different kind of shadow. Let's go to the next slide if we could. Oh, that's the total eclipse. And you can see that the total eclipse up here, as it says, occur about every 18 months. Every 18 months, we get a total solar eclipse. Next slide, please. And here it is. Remember the straight, and the astronomers have it's called syzygy. Syzygy. That means everything's in a straight line. Okay, here you have the sun, the moon, and the earth in a straight line like this, and you're going to get a total solar eclipse. Again, Earth orbit counterclockwise, moon's orbit counterclockwise, and then here we talk about the umbra. That's the dark part of the shadow, and the penumbra, that's over here. I mean, there's the penumbra, and that's where you get the partial eclipses. So unless it's in the umbra, you won't get a total solar eclipse or an annular eclipse. Next slide, please. And then here's the umbra right here. And what happens, the umbra has different links. And sometimes it won't reach, the shadow won't reach the earth. And sometimes it's big. And so we'll look at that. Next slide. Okay, so here's the next, this is the annular eclipse. Notice here's the shadow, here's the penumbra, and it comes to that point right there. That point right there. I'm sorry, but that's where the earth and the moon and the sun are exact sizes. And the shadow continues on. And that's why when you look down here, you don't get a moon as big as you did when you get a total eclipse. So that's an annular eclipse. P-A-T. Okay, next slide, please. Okay. Talks about the antenna. That's what I mentioned just a second ago. Next slide, please. And there's a picture of it. An annular eclipse occurs every 1 or 2 years when the sun and the moon are exactly in line with, but the moon is, apparent size of the moon is smaller than that of the sun. And because of that, you get the annular. The last annular eclipse was last October, and I was going to help with that here in the city, but guess what? It was cloudy. So that happens here. I go out to look at comets and everything, always cloudy. Next slide, please. And then here's the one here. This is the fourth type. This is a hybrid eclipse. Look at the shadow here. It's long enough. It touches the earth. And so you have a total eclipse. But going on down here, now it's farther away and it can't touch there. And so you have an annular eclipse. Next just shows a diagram of it going like this. And so the curvature of the earth has a lot to do with, what kind of eclipse we get as well. Next slide. Okay. Magnitude. This is one of the most important words you need to know before you leave today. Magnitude. Magnitude refers to how much of the diameter of the moon is covered, or the diameter of the sun is covered by the moon. So that's what that means. And usually you don't get total eclipses unless the magnitude is at least 1. And for us, on this particular eclipse on April the 8th, notice that the umbra, or the magnitude, is 1.05, which means that the moon is 5% bigger than it is, normally, because you have to have one for an eclipse. But actually, by the time the moon and the eclipse gets here, the magnitude is down to 1.02. So it's lost a little bit of distance, but it's not all that bad. Next. All right. So the higher the magnitude number, more than one, a total solar eclipse will be longer than an eclipse will last. And the area it can be seen from on Earth will be larger. Higher magnitude tend to confuse of the solar corona, planets or stars. But on the other hand, the phenomenon, we're going to talk about this, Bailey's beads, the chromosphere, and shadow bands, they will not be seen as much as if it was a smaller magnitude. Okay, so on this particular eclipse, if you want to see shadow bands and that type of thing, you should go closer to the edge of the shadow, and we can find that if you want. Next slide. So here it is. Notice over here that the moon is halfway across the sun, so the magnitude is 0.5, and over here it says the occultation is only, what is it there, 0.39. There's more area that's not covered, but as long as they're uniform, and most eclipses always refer to the magnitude as for the accurate part. Next slide, if I may, please. And here's obscuration, and that you just use mathematical formulas to figure out, how much of the particular body is covered. Next slide. Okay. Next slide. Eclipse cycles. All right. Now, so far, we've talked about the synodic period, 29 and a half days, and we have the anomalistic, 27 and something to draconic. Remember, those were the three. Remember this one here? Synodic was the moon going around the earth, coming back to the same phase. The anomalistic was going from the closest point, perigee, back to perigee. And this one here was the draconic, was going from the ascending node here all the way back to the ascending node, if we may. Okay, so here are the three again. A anomalistic moon and a draconic moon. And if you figure everything out, it's hard to believe, but an eclipse occurs every 18 years, 11 days, and 8 hours. That, I didn't give you I don't have it in my computer out, but those others when I showed you all those others earlier of the eclipses for this year, each one of them had a different Saros number. So, okay, that's called the Saros cycle. And look at this. We're apart. The moon that you're going to see with the eclipse this time is in the Saros 139. Now look at this. It had its first eclipse in May 17th, 1501. So the moon that's going to cover our sun on next Monday, it's had its first eclipse, and its last eclipse is going to be on July 3rd in the southern hemisphere, 2763. So the series lasted 1,262 days. There's been 71 eclipses in that. There will be 71 eclipses out of Saros 139. Now look down here. The first seven eclipses were all partial. The next 12 were all hybrid. And notice now we're going to have 43 total eclipses in a row, and then back to 9 partial. And they all occur at the ascending node. And there's about 40 series. There's about 40 different Saros numbers. And each of those numbers for that particular moon, that changes when it's going to happen for everything. Next slide, please. And here's just a drawing showing. And remember, if it moves the 8 hours, it also, from one eclipse to the next, the eclipse shifts 120 degrees. Okay? So here is 1824, And here is 78, that's 54 years. And you can see, here's where this one is in 24. Here's Mexico, we're up here, and over here. Notice it's still in the area, but see how it's moved south from this one? It's moved south, so you can see it there. So next slide, please. And so I just wanted to show you a problem. The last eclipse of this particular Saros 139, we're member 30, this is member 29, and here was the date, March 29th, 2006, and here was the time, here was the location. Okay, so let's add 18 years to 2006. So the year, we're going to have an eclipse in the year 2024. That's the 18 years, see that? Now over here it says add 10 days. Well, you said 11 days. Well, I didn't tell you the whole truth. There's 18 common years in a 18-year period. You need to know that 18-year period, how many leap years were there? And so the leap years change it. So this time we have 5 leap years, 2008, 12, 16, 20, 24. And that's why you only add 10 days. So if we add 10 days to the last date, by golly, we're eclipse on April the 8th. And the greatest eclipse time, well, it was 10:12 before, so we have to add 18 hours to it. And the location, okay, right, doing this one was minus 16, okay, and so you add 120 degrees west, and it comes out that the next location of the greatest eclipse day will be at 103. Next slide, please. Now look at this. This is, okay, April 8, 2024. We estimated that, look at that. We estimated 100, I can't see that real well, 103.3, and it was 104.1. And we estimated the greatest eclipse would occur at 1812. No, it's at 1818. And that's don't you think that's pretty accurate for an 18-year period, how you can do that? So just remember 18 years, 10 or 11 days, depending on the thing, and add 8 hours. And the 8 hours you add for the time, and 8 hours you add for the 15 degrees that the next eclipse will move to the west. I just think it's fantastic how they have, and these three different things, the three different, the draconic, the anomalistic, and the synodic months. It just works out. They all work together. Next slide, please. Okay, this is where Emily does so much for us in getting these pamphlets all done for you today. And Emily's a great person to work with, and I really enjoy working with you, Emily, so thank you. Anyway, what we're going to do now, I'm going to show you some websites. This is the first one. This is the Naval Observatory in Washington, D.C. I've only looked through the telescope in there 3 times, I think, in Washington at the Naval Observatory. However, this is a picture of it in 1863. This picture you see is the Naval Observatory, and I don't know if you know D.C. very well, but the observatory at that time was located in Foggy Bottoms. And that was a terrible place because they constantly got malaria. It was just infested with all sorts of things. But on 1863, it was in August, I think it was August 23rd, Asaph Hall, who discovered the 2 moons of Mars and named them Phobos and Deimos, fear and terror. And he did that by reading the Iliad. I think it was book 5 of the Iliad. And he selected those 2 names for Mars from what Homer wrote in the Iliad. But anyway, there was a knock, and he opened the door, and who should be there but Abraham Lincoln and Joseph Hayes, or Joe Hayes, who was his secretary. And they wanted to come over, and so what Asaph Hall did that night, he showed them the star Arcturus through the telescope, and he showed them the moon, and they both left. And it was 5 or so days later, he heard another knock, and he opened up, and there was Abraham Lincoln by himself. And he came over for one reason. He couldn't understand when he looked through the telescope that the moon was upside down. And so Asaph Hall explained to him about, the refractions and so forth. Believe me, I got other stories I could tell you about Lincoln and his understanding of the stars and things. He knew the stars very well, and quite a fantastic person. The other thing that impressed me was that when he went out, he never had the military with him. He said, I'm the people's person. And he'd walk, through the streets and shake hands with people. What a person he was. So anyway, because of, they built a new facility in a different part of Washington, D.C., but unfortunately it's closed now because that's the site where the vice president has her home right now. So that's the site of the vice president's home, so they don't open up to the public like they used to. Next slide, please. Okay. Oh, it's going to be kind of hard to. Okay, but anyway, when you click on that, you'll go right to this site right here. It says eclipse, location label, height. And what you can do up here is to request, if you don't have all the data, all you have to do, believe me, these are not hard to use. Okay, you just type Avon Lake right here, and that's and when it prints up, it'll say Avon Lake. The height is what is it? 100 and some meters tall. That's our altitude here. It's about 500 feet. In fact, it's interesting to note that where I touched Avon Lake on the slide, it said that Avon Lake, depending where we were, was only 470 feet from the central part of the path of totality. 470. Next slide, please. Hopefully. And go to the next slide, if you would. This one's better, I hope, for you. And notice Avon Lake, latitude, longitude, and so forth. And here you can see the eclipse begins at 17:53:42 seconds. What in the world is 17? That's universal time. And all astronomy things goes on to universal time. And universal time begins in London, about London, and we're 5 hours behind, so when it's 3 o'clock in London, it's 10 o'clock here in the morning. However, when the United States goes on daylight savings time, there's only 4 hours difference, okay? So normally there's 5, but because we went on daylight savings times, there's 4, and so you have to subtract 4 from each of these numbers. So if you go up here to here, this is 17. If I subtract 4, I get 13. What number is that? What time is that? 1 o'clock, right? 13 on a 24-hour clock, it's 1 o'clock. So the eclipse in Avon Lake begins at 1:58:42. Totality begins at 1:13, and maximum is at, again, this is 3 hours. This is 3 o'clock. 3:15 will be right in the mix of the eclipse, and it ends at 4 from that, that's 16. That's 4 o'clock in the afternoon. So the eclipse is over at 4:28. So that's what you're going to be seeing. And I hope you'll use the pamphlet that Emily did on the backside. She can tell you about what's there. Next slide, please. Okay. Oh, you can't see this one at all. Well, there's one thing I want you to do. I haven't asked you to do too much, but the next time you go out and you see the moon, I want you to pinch it. Okay? How big do you think the moon is in the sky if you pinch it together? I think you're going to be surprised. It's about the size of a pea. No matter if it's on the horizon or up in the sky, it's going to be about the size of a pea. Now, what I try to do here, there's also on here, up in this area, you can see the Big Dipper. And when I put the Big Dipper in here, it's to show you the angles. In other words, has everybody seen the Big Dipper before? All right. Now I want you to watch here. So this is 5 degrees. So I can take my hand and that's 5 degrees, and sometimes I'm out walking in the afternoon, I want to figure out how soon the sun's going to set. 20 minutes, 20 minutes, 20 minutes, 20 minutes, 20 minutes. So you can kind of estimate, figure out where the sun's going to land, and because 1 degree is equal to 4 minutes of time, okay? So this is here, and you can see that it goes 10 degrees here, 15 degrees out here, and then here's azimuth and altitude. Now for the eclipse that we're going to have, the altitudes are going to be here, it's hard to see, and the azimuth is going to be here, but it's 44 degrees, I think, it's something like that. So here, azimuth. Every one of these star charts I have, or this chart you get, azimuth. So I'm facing north. That's 0. I turn clockwise 90 degrees. 90 degrees is east. Then 180 degrees is south. 270 degrees is actually west. So if you watch here, you can see that the azimuth for the total eclipse is going to be at 222 degrees. So here, 180, and over here, that's 270. So 180 and 270, that's 90, so it's about 45 more. So that's about 225 degrees, so I turn a half a degree. And so you can see that's where that's going to be. And the altitude is about 44, I can't remember, 48.9, something like that. So 0, 90, 45, up a little bit. So in case you're trying to kind of pre-screen where you want to watch the eclipse, we'll go out there print this chart and go out and make sure that if there's trees are there, that they're not going to block your view. Okay, next slide, if you may. And here I just put 2, and you can't see them very well, but what it points out, that the time in Avon and Avon Lake only vary about 3 seconds time. Even if you went to North Olmsted, it's the minor difference in time. So we're all pretty much close to the center of the eclipse, or the path of totality. Next slide. And then, okay. Then there's one thing it talks about vertex and so forth. And what I did here was just to show you that if you go to vertex angle, it's measured from the point on the sun that has the highest location. And so here it is. And on your charts, it'll give you these 2 numbers. And so the first is 12.2, and down here is 221. And so by just doing this, you can predict on eclipse day, you can see where the sun is going to come in and go across the sky. It's going to start here at 221, and it's going to exit the sun at 12.2. Next slide. And here I tried to show it to you. In other words, down here, see right that little bump right there? And that's where the eclipse is going in. And I'm going to show you a website next slide that'll show you all of this. Next slide. Oh, where to observe. Here's a group of people looking up towards the corona. Next slide. Here's another group. They're out in California at Griffith Observatory. Next slide. That's Nathan and Connie. I've seen them so many times. His shirt's got dirty since I started. That black spot, I don't know what happened. Maybe he's got tired and spilled part of his bubbles. I don't know. But anyway, everybody, you have to decide where you want to be. Where do you want to be? Who do you want to be with? Because eclipses are very special. Next slide. All right. You must remember to always wear glasses during the partial phase. Remember, I showed you the partial. And during totality, when it finally gets dark, and you know the time now, you can take your glasses off during that. But and it'll be pretty safe there. Next slide. Okay, this is the next slide. This is the next slide. This one here is called, I can't even remember, I think it's astronomy.org or something like that. But anyway, it's on that thing that Emily prepared. And so you're on eclipse simulation. Then you want to go down and make sure you choose the right eclipse. Because, so April 4th, and then it opens up. Next slide. Then you get a thing and you put up here where you want to be. Okay, over here. Next slide. And there it is. And it's amazing what you can do with this. You can spend hours with this simulator watching it because I'm always look, this bar right here, this moves it from the beginning of the eclipse to the end of the eclipse. This bar right here fine-tunes the eclipse, like you want to move in slower. Over here they have a zoom bar, okay, so you can make it bigger. You already got it for your own town, and then I'll show you later, but here you can do the shadow. In other words, if you click that and run it, you can actually see how the shadow is going to come for your house, okay? You can see it, and that's kind of fun to watch. And then over here, you can see Bailey's beads right there too, and you can even magnify it a little bit. We're going to talk about Bailey's beads in a minute, but you can do that, and you can turn on the map, and you can do lots of things. Believe me, if you go there, you're going to have lots of fun. Next slide, please. And there you can see how I zoomed in to make it a little bit bigger. Next slide. Okay. And then over here's the moon, excuse me, the sun. And there's some sunspots there. But make sure you're wearing your glasses when you look at the sun. Don't do it without it. I don't want you to injure your eyes. Next slide. Okay, the surface temperature is about 10,000 degrees, 6,500 degrees. And the sun has an 11-year cycle. And this is cycle 25. Now just think, they have been plotting the sunspots for 25 times 11 years. And so we have an accurate record of how many sunspots and everything. Next slide. Okay. Now what this is probably trying to point out, if we have a lot of sunspots, the corona should be pretty round, okay? It's going to be probably pretty close around the moon there. So that's, next slide. Now here you can see with the minimum, see how it comes out more out the side. So I would predict we're going to have a circular corona. Next slide, please. Okay. These are the different, you should know these. First contact. Remember that one slide showed you where the first bite of the sun? That's first contact. This is second contact. The second contact is when the moon has moved off almost all across the sun, and you've got what's called the diamond ring effect. Then here's totality. And now notice the moon is moving on that direction because the moon is always going to your left. That's the third contact, and then finally when it goes out completely, that's the fourth contact. So you're going to hear those terms, first, second, third, fourth contact. Next slide. Okay, and then notice here, this is that same slide I showed you earlier, but now notice I told you that you can click on the shadow too, and you can see the shadow moving up, and you can see right here I have it set, which is about maximum for us. The other thing that's important to note, that all around the horizon, beautiful pictures. I mean, you can take beautiful pictures of the horizon is just magnificent. Next slide. Okay. Don't know who that is, but anyway. Here's the corona. This is what it's going to look like. Okay, now you're going to see Venus right here. That's going to be really, and if you look towards the shadows and you keep watching, you'll see Venus before you see anything else. So if you suddenly see a bright object up in there, you're looking, that's the planet Venus. Here's the corona, and then going way up here, here's Jupiter. And if you have powerful enough glasses, right beside it is the planet Uranus. And then over here, down here in this corner is Mars and Saturn. And notice up here, we're going to be able to see a comet as well. So if you bring your glasses and you're going to see a comet. Next slide. Okay, here's a picture of the comet. Right here, comet 12P Pons Brooks, okay? There's the comet right there. Next slide. And you can see that it was discovered in 1812, rediscovered, and that's enough information on that. Next slide. Next slide. There's one of the pictures. Isn't that beautiful? But that's what it's going to look like with the horizon. That's why I'd like to get out where, you know, you have trees and open space and get those beautiful pictures. Next slide, please. And here's another one. This one was in Norway. Look at that. Isn't that gorgeous? Next slide. And over here, we don't have time to do it, but somehow, but it just shows you at each point, like right here, what's that say, 4 minutes? Okay. You can see that the sun is only 3.5% as bright as it was when it started. When you get down here to 75 seconds, now it's only 0.2%. So, you know, you think nothing's going to happen, but then all of a sudden it picks up and it gets dark. And the other thing, when it gets dark, as it gets dark, you're going to be able, you can see every hair on your hand. They just shine, and so you can see them. Next slide, please. All right. And here are the shadow bands. Now, the shadow bands, we may not see them as much, but a shadow band, because we have a crescent sun, you know, because we don't have much light, that crescent sun now going into our atmosphere, it produces waves. You know, it's not solid, but it's waves. So these are called shadow bands, and they're also affected by temperature, humidity, density, and pressure. But again, if you're farther out from the center, you're more likely to see these. Next slide. Okay, here it is. Now watch the sun. You know, the shadows coming in. Next slide. And then I wanted to show you this. This is the Lunar Reconnaissance Orbiter, and it flies 31 miles above the moon's surface, and it took a profile. There's the moon's profile. Notice how it's all pointy and juggly all the way around. Next slide. And normally you see it like this, but it's really like that. And it's irregular. Next slide. So it affects, look at this. Look here. All here. All here. It keeps getting narrower and narrower. And these are the Bailey's beads. Next slide. But finally, there's only one opening. And when the sun goes through that last opening on the surface of the moon, you get the ring effect, like a diamond ring. So that's the ring effect. And you'll see that, and it's kind of interesting. Next slide. Okay, what is this? Oh, the chromosphere around the edge is red. Okay, next slide. And you might see also a solar flare right over here, because the sun's been pretty active. And the solar flare is actually attached to the photosphere that we talked about earlier. Next slide. Next slide. And the corona here. The reason it's, notice that the corona reaches high temperatures, but it's very less dense. And it's interesting, if, as far as temperature, you know, if you go camping, you sit next to the fire and you're nice and warm, you know, but here, you're right next, and as you move away from where you were seating, it gets hotter. So the corona is very hot, and that helps spew all those electrical ions out into the universe. Next slide. Another picture of, okay, next slide. We're almost through. Here it is, totality approaches. Chromosphere, totality ends. Okay, those are the things. Next slide. And here now, after the totality begins to end, watch the clouds go, you know, away from you. And that's about 5 minutes after totality. Next slide. Next slide. Well, the pigeons are back to work. And then the next slide, this is the path of totality. Next slide, please, Jay. And here you can see the path of totality. This is an A. That's totality. Here's a B, C, D, or whichever. This is a one. Finally, this is the last one. You can see that if you're farther away, you're not going to see as much. You can see the partial eclipses. Next slide. All right. This is a nice one too. Well, it's just showing the shadow. And you can see that when it went by, it was traveling 2,160 miles. And in our area, it was 112 miles wide. Next slide. And that's the penumbra. And notice, I always like to see it when it's real round, and that's when it's closest to the Earth and everything. And notice that it's going to occur at 2:18. And notice that it is going to be 4 minutes and 28 seconds, and we're about 3 minutes and 55 seconds. Next slide. And then here's this path of totality. They're estimating, people that do estimation, that on the 7th or 8th, we should have anywhere from 139,000 to 550,000 people come into Ohio. Next slide. And here is this is what traffic might look like. This is a picture of Tennessee, and it's a picture of Nashville. They were estimating 100,000 people that day, but 300,000 showed up. 300,000. Think what would happen. My gosh, I don't know. Here's the next slide. And here's in Lebanon, Missouri. If things got so bad, everybody stopped and had their picnic right there on the highway. So you got to be adaptive. If you're going to go chase it, you got to do it early, or, next slide. Here it is. Here's the center path. Here's Avon Lake right here. Next slide. And here, if you go by this issue of Astronomy Magazine, the April issue, it has this map in it showing you the times, which you can't read. This is 1 minute, 2 minutes, 3 minutes. Same down here, 1 minute. Okay. And we're right up here in 350 area. So it shows you along those lines, where you might want to go. This one's a kind of a neat one. I like this too. Next slide. And so after you go through and you punch it, I did it for Avon Lake. And notice, you can't read the signs here, but it gives you all the information for each town, and then I got a couple more. Next slide, please. Okay, this is a weather one, talking about the weather, that we have about a 70 chance, 60, or we're up in this area here for cloud cover, about 70% over the past next number of years. I don't remember. Next slide. Okay, here's another weather one, and make sure you go there. Next one is a weather one, but make sure you go to the weather page, and it'll be easy. Once you go into it, you can find it. Next slide. Okay. And then the protection, we've talked about that. Next slide. And don't forget that even the cat wears the glasses. Next slide. And by the way, as you leave tonight, every one of you is going to get a pair of glasses. And also make sure you get Emily's publications there that show things. Okay, next slide. All right. Okay. Now, be careful with your cameras and your iPhones. Be careful taking pictures. Go on there, you can buy little things you can put on your iPhone that you can take pictures, while the sun's out. May not be as bad as when it's dark, but I would not use your iPhone to photograph partial eclipse. Next slide. Next slide, please. And this is what you need to have handy. Sunscreen, insect repellent, a nice chair, a hat, bring your glasses if you want, your umbrella, bring a camera, your binoculars, bring that food, gasoline, and probably one of the most important areas is up here. All right, next slide. All right, and here are all the slides here are the websites that Emily put on for you. Next slide. And I just wrote, there are many that agree that a total solar eclipse is one of the most awe-inspiring natural events that one can personally experience on Earth. Those of us in this area are so fortunate to be a part of this very special occasion and very special event involving the sun and the moon. Don't feel embarrassed if your eyes tear up during the totality, or you want to cheer to express your feelings or astonishment, because that's how you celebrate a total solar eclipse. So I hope all of you enjoy the eclipse as you can, and all those that are watching at home, again, Josh, thanks for setting everything up for the presbytery. So you're free to go. I'll be up here if you have any questions. Well,